Okay, continuing on with Chapter 4, we're going to be looking at indeterminate forms and L'Hopital's rule, which is a very important rule and allows us to take a whole bunch more limits than we would otherwise normally be able to take. So let's start with this idea of indeterminate forms. What do we mean by an idea of an indeterminate form? Well, for example, if we're taking a limit, and let's say we're taking the limit as x approaches 0, let's just say it's x squared minus 4. Actually, let's not approach 0, let's approach 2 over x minus 2. Now, there is a way we can actually do this limit by factoring the numerator, but I want to look at an alternate way. And I want to show you what I mean by an indeterminate form. If you notice, what this tends towards is, well, 2 squared minus 4 is 0. So you get a 0 in your numerator if you plug in 2. And so it's heading towards 0, the numerator is. And as x approaches 2, the denominator is also heading towards 0. So this 0 over 0 is an indeterminate form. Okay. Now, you can also look and say, what happens if I take the limit as x approaches infinity of x squared over 4 divided by x squared minus 4 over x minus 2. Well, here as x heads off to infinity, infinity squared is infinity, and infinity minus 4 is still infinity. This heads towards infinity in the numerator and infinity in the denominator. So this is another indeterminate form. These are the two main types of indeterminate forms, when you have a limit that heads towards 0 over 0 or a limit that heads towards infinity over infinity. And in either of these cases, one way that you can take this limit and try to evaluate this limit is by using L'Hopital's rule, which says basically this. It says if we have a limit as x approaches some value a of a function f of x over a function g of x, and this approaches either 0 over 0 or it's possible it could approach infinity over infinity. This is one of those indeterminate forms. So if this is the case, then what we can do is say, alright, we'll take the limit as x approaches a of f of x over g of x, and that will actually equal the limit as x approaches a of the derivative f prime of x over the derivative g prime of x. And you can actually keep going from there. If this is also an indeterminate form, you can keep on going from there. In other words, you can take the derivatives, and let's see how that can actually help us. If we go back to our original example, the limit as x approaches 2 of x squared minus 4 over x minus 2. Well, again, this is an indeterminate form. We get to 0 over 0. So this is going to equal then, by L'Hopital's rule, the limit as x approaches 2 of the derivative of the numerator, which is just 2x, over the derivative of the denominator, which is just 1. Alright, and now you can see you can plug 2 in. This function here is continuous and defined at 2, so it's 2 times 2 is 4 over 1, or just 4. Now remember, you got the same thing. We could have done this one. We've done limits similar to this already. That's the limit as x approaches 2 of x plus 2 times x minus 2 over x minus 2, and we would just go ahead and divide those factors out and got the limit as x approaches 2 of x plus 2 over 1, which is also 4. So there's an alternate way to do that particular example, but we get the same answer in this case of 4. We got it using L'Hopital's rule. Let's look at that other example where we have the limit of that same function as x approaches infinity and see what happens. We take the limit as x approaches infinity of x squared minus 4 over x minus 2. Here this is an indeterminate form of infinity over infinity. So this will equal, according to L'Hopital's rule, the limit as x approaches infinity of the derivative 2x of the numerator divided by the derivative of the denominator, which is 1. Well, now the denominator is getting huge, so the numerator is getting huge while the denominator is standing still at 1, and so we get actually infinity here. Basically what you can see is happening is you head off to infinity. The numerator is heading towards infinity much faster than the denominator. That's really what this tells you. Your derivatives tell you how fast things are changing. So that's why we take the limit of the derivatives to see which one's changing faster, and the numerator is changing faster than the denominator. And if the numerator is getting bigger faster than the denominator, well then the whole thing's going to go to infinity. If the denominator is getting bigger faster than the numerator, then we're going to head off towards 0. Okay, so there's a couple quick examples. We'll look at plenty more, but I want to look at a couple other types of indeterminate forms that we can use L'Hopital's rule for. The first is what's called indeterminate products. And that is, suppose we have the limit as x approaches a of some function f of x is 0, and the limit, as x approaches that same value of a of another function g of x, is infinity. So one's heading towards 0, one's heading towards infinity. Well, what would then be the limit as x approaches a of f of x times g of x? I mean, this is approaching, this isn't really what it's equal to, but it's approaching a 0 times infinity. What is 0 times infinity equal? Well, we don't know. We can't multiply by infinity. Infinity is not a number. We always say that 0 times any number is 0, but infinity is not a number. Infinity is a concept. It's a goal. It's a place you head towards as you get bigger and bigger. So we can't say what that is. So this is another indeterminate form when you have 0 times infinity. Alright, so this is yet another indeterminate form. 0 times infinity. Now, how do we tackle that? Well, determinate form. We can say that the limit as x approaches a of f of x times g of x is going to be the same as the limit as x approaches a. Well, we have a couple of choices. We can either say it's f of x divided by 1 over g of x, right? Because if you take this and you divide by this fraction, you flip it up, you have f of x times g of x. Now, what does that go towards? That tends towards, we said f of x is going to 0, and since g of x is going to infinity, 1 over g of x is also going to 0, so you get that indeterminate form. Or you could say that this is the limit as x approaches a of, you could say g divided by 1 over f. Now g is heading towards infinity. Since f is heading towards 0, 1 over 0 heads towards infinity. So by rewriting it this way, you get one of these two original indeterminate forms, and then once you have that, then L'Hopital's rule applies. So once you get it to one of these original indeterminate forms of 0 over 0 or infinity over infinity, then you just go ahead and apply L'Hopital's rule. Let's look at an example of one using the indeterminate products. How about number 20? Do 26. 26, we have the limit as x approaches. Actually, let's do 25 instead. 25, we have the limit as x approaches 0 from the right. All these rules apply again if you approach a from the left or from the right. So the limit as x approaches 0 from the right of the square root of x times the natural log of x. Square root of x times the natural log of x. Now, what happens as we go towards 0? Well, this tends towards the square root of x. Well, the square root of 0, that goes to 0, times, what happens when you take the natural log of x and x starts heading towards 0? Remember what the natural log function looks like. It looks like this. So as x approaches 0, the natural log function takes off towards negative infinity. So we have an indeterminate product of 0 times infinity. It's okay that it's negative infinity. So what we're going to do is we're going to try and rewrite this so we can get one of those indeterminate forms and use L'Hopital's rule. So this is going to be equal to the limit as x approaches 0 from the right, and maybe I'll do it this way. I'll take the square root of x divided by 1 over natural log of x. Alright, now what happens here? Well, this now tends towards 0 on the top, and if natural log of x is tending towards negative infinity, 1 over that is tending towards 0. So now we have an indeterminate form of 0 over 0. So now we can use L'Hopital's rule. So then this is equal to the limit as x approaches 0 from the right of, let me just write it this way, as x to the 1/2 on the top, and my numerator, instead of natural log 1 over natural log of x, I'll write it this way, natural log of x to the minus 1 power. So by L'Hopital's rule, because that's an indeterminate form of 0 over 0, we can say it's equal to the limit as x approaches 0 from the right of the derivative of the numerator, that's 1/2 x to the negative 1/2, times the derivative of the denominator, which is negative natural log of x to the negative 2, times the derivative of what's inside, which is 1 over x. Alright, so what does this equal? Then this is 1 over 2 times the square root of x divided by negative 1 over x times natural log of x quantity squared. Alright, and so what does that equal then? Well, this is the limit as x approaches 0. It is, keep your limits in. So we have the limit as x approaches 0 from the right of 1 over 2 square root of x times the natural log of over 1, the negative of all that. So I just brought this denominator and flipped it up. What we have at this point then is actually kind of messy, because you can see we haven't really made much progress here. We can say this is a limit as x approaches 0. I could take x divided by the square root of x, which will leave me the square root of x on top, times the natural log of x squared over 2, the negative of all that. This really hasn't got me very far at all. I still have a 0 here times a negative infinity, and I'm back to that indeterminate form. So that happens sometimes. Sometimes you try one thing and it doesn't work out, or at least it doesn't work out as easily. So I'm going to do this again, this same problem, only I'm going to switch it this time. This time I'm going to take the square root of x and drop that to the bottom as a reciprocal. So here, let's go back and let's say the limit as x approaches 0 from the right of the square root of x times the natural log of x is equal to the limit as x approaches 0 from the right of, let's see, we're going to take the natural log of x on top and 1 over the square root of x in the denominator. Okay, so this is the same thing algebraically. And so this is equal to the limit as x approaches 0 from the right of the natural log of x. And of course, what does this tend towards? This goes to an indeterminate form. This is a negative infinity over, this is heading to 0, so the denominator is heading towards infinity. So it's an indeterminate form, so we can use L'Hopital's rule. Right now I'm just going to rewrite my denominator as, let's see, 1 over x to the 1/2 is x to the negative 1/2. Now, by L'Hopital's rule, this is equal to the limit as x approaches 0 from the right of the derivative of the numerator. Derivative of natural log of x is 1 over x, divided by the derivative of the denominator, which is a negative 1/2 x to the negative 3/2. So I have the limit as x approaches 0 from the right of 1 over x divided by negative 1 over 2 x to the 3/2. So let's flip up this. Let's divide these two fractions by multiplying by the reciprocal. And what do we get then? A negative 1 over x times 2x to the 3/2 over 1. Okay, so we had 2x to the 3/2 over x, so x to the 3/2 minus divided by x to the first will leave us with just an x to the 1/2. So we get a negative 2x to the 1/2 is what that reduces to. And so now as 0, as x tends towards 0, negative 2 times the square root of x also goes to 0. So the limit is in fact 0 of this function. And you can see that graphically. I went ahead and put in the function the square root of x times the natural log of x, and you can see as x approaches here 0, what's happened to the function? Well, it comes down here, and as it makes it turn up here, it's actually heading towards 0. We can kind of zoom in on that, maybe. Let's see. Yeah, you can zoom in. You can see that the graph is actually turning up towards 0 as x heads towards 0. So the limit of the function is 0 at that point, even though the function is undefined at 0, because again we can't take the natural log of 0, so the function is undefined there at x equals 0, but the limit of the function as x approaches 0 from the right, again we have to approach from the right because we can't take the natural log of a negative number either, is actually going to be 0. The function heads towards 0. Alright, so there's an example of that. Okay, a couple more indeterminate forms that we want to look at. The first one is indeterminate differences, and again this is just out of your reading here, so just to reiterate what you read, we have the limit as x approaches a goes to infinity, and the limit as x approaches g or a of g of x. So the limit as x approaches a of f of x is infinity. The limit as x approaches a of g of x is infinity. Then what can we say about the limit as x approaches a of f of x minus g of x? Well, can we say it's infinity minus infinity? No, that doesn't really make any sense. We don't know how to evaluate that because the f of x infinity might be growing faster than the g of x infinity. Again, it's a struggle. Which one's going to infinity faster? And so it may be 0. It may be some compromise between the two. Maybe some finite number. We don't know. So we need to turn this into an indeterminate form. Like, for example, number 33. If we look at number 33, I don't think you have one exactly like this on your homework, but we'll take a look at the limit as x goes to infinity here of x minus natural log of x. Alright, this is not equal to, but it tends towards infinity minus infinity, right? Because as x goes to infinity, obviously x goes to infinity, and as x goes to infinity, the natural log of x goes to infinity. So we need to try and put this into an indeterminate form. So we're going to take the limit as x approaches infinity of x minus ln of x, and we're going to say that's equal to Kind of a little trick here. What we're going to do, we're going to say this is a limit as x goes to infinity. I'm going to factor an x out in both of those terms, so I get 1 minus the natural log of x over x. Now, what does this equal then? Well, as x goes to infinity, obviously this portion goes to infinity. What about this portion right here? Well, let's just pull that out to the side and look at the limit as x approaches infinity of 1 minus the natural log of x over x. Here we can use limit laws, because we have the limit as x approaches infinity of, well, 1 minus the limit as x approaches infinity of the natural log of x over x. So here we have an indeterminate form. So by L'Hopital's rule, which we can sometimes put an h above the equal sign to indicate we're using L'Hopital's rule, we have the limit as x approaches infinity of 1, which of course is just going to be 1, minus the limit as x approaches infinity. By L'Hopital's rule, we have infinity over infinity here, this portion. So we're going to have the derivative of 1 over x over 1. As x goes to infinity here, this goes to 0. This part goes to 0, so we get 0 over 1. And so we end up with, then, 1 minus 0, or 1. And so the limit then as x approaches infinity is equal to this infinity times 1, or just infinity, because all this here in the box went to 1. Alright, by L'Hopital's rule. Okay, a couple more type indeterminate forms, and that's going to be indeterminate powers. And there's basically a couple of situations we need to look out for. Take the limit as x approaches a of f of x to the g of x. If that goes towards any of these types, either 0 to the 0, or infinity to the 0 power, or 1 to the infinity power. Those are indeterminate form, and we're going to need to use, a lot of times we'll use logarithmic limits to evaluate those. We'll look at some examples of those in the next video.